Okay, now let's apply one of the explicit Adams methods, which, remember, all of the Adams methods are stable and therefore guaranteed to converge because they're also consistent. Let's apply a third order explicit Adams method to the following problem: u prime equals minus 1000 u plus sine of t. The exact solution is actually almost exactly 0.001 sine of t, so the exact solution is just almost a multiple of sine and nice and smooth. And yet when we apply the third order Adams explicit method to this problem, we get some very strange results. With n equal to 100, which means h is 0.01, we get overflow. It looks like it's totally unstable, and yet we know all the Adams methods are stable. You cut n to 0.001. Remember, we're trying to approximate basically the sine function. With a step size of 0.001 is still totally, it appears to be completely unstable, and until you get to a certain value of h, about 1 over 1800, and suddenly it works just fine. So there's a real sudden transition between values of h for which it appears to be completely unstable, even though we know it's a stable method, to where it works fine. It's a dramatic sudden change from terrible to great. So what is going on here? Well, let's go back and look at our key error bound in the stability theorem. It says that the error at a fixed point is less than this times the maximum of the errors made by the starting methods times the truncation error. Well, the problem is right here, e to the constant times absolute value of a times t. This actually was derived not for the general problem, general nonlinear problem u prime equals f of t and u, but rather for the linear problem u prime equals au plus f of t. We didn't derive it for the general nonlinear problem just because it's so much simpler for the linear problem, but you can get a similar bound for the nonlinear problem. In that case, a would be replaced by the partial of f with respect to u, but our problem is linear, and it looks just like this with a equal to minus 1000. So in the error bound, you see we have this huge exponential that's e to the some constant times absolute value of minus 1000, which is 1000t. So you've got a large exponential term there. That's the source of the problem. You've got an error bound that says basically the error is less than infinity because this exponential is so huge that essentially doesn't matter how small h is, the truncation error would have to be astronomically small before this would start getting to be reasonable because this exponential is so large. And the reason the exponential is so large is because the absolute value of a is so large. So we call a problem stiff if the absolute value of a, in the linear problem, the absolute value of a is large. Now, usually it's only called stiff if a is large and negative. Why? Because if a is large and positive, the solution itself is going off to infinity exponentially, so you expect the error to be large. But if a is large and negative, there's no a priori reason why you shouldn't be able to approximate it accurately. In other words, this error bound is artificially large, something we ought to be able to get around because the solution is nice and smooth. In fact, in our example, the solution was basically constant times sine of t. There's no reason why we shouldn't be able to get good accuracy using a reasonable step size, and yet we weren't with the explicit Adams method. And if we try Euler's method, the same thing happens. It's terrible results. Seems to be completely unstable until h gets below a certain threshold, and then suddenly it works fine. And why is that happening? Well, it's this exponential term which is essentially infinite. Now, the reason it finally starts working is not because the truncation error, the h gets so small that this compensates for that. No, this term, the exponential, is so large that it doesn't matter essentially how small h is, the right-hand side is still going to be essentially infinity. So why does it suddenly become good after a certain after H goes below a certain threshold. Well, to see why the explicit third-order Adams method and Euler's method and other explicit methods do just fine after H gets below a certain threshold, we'll never figure it out by looking at that other formula with the exponential term in it, because the exponential term is so large that it's essentially just saying the error is less than infinity. Here's another error bound that was derived in section 1.3 that does not have the exponential term in it. Notice this says the error is less than a constant, no exponential, no a there, times the same thing as the other error bound, the truncation error and the maximum of the errors due to the starting methods. But this error bound only holds when AH is in the region of absolute stability for the multi-step method. Now, what is absolute stability? Well, notice that a method is either stable or it's not. Absolute stability, you don't say a method is absolutely stable or not absolutely stable. A given method would be absolutely stable for some values of H and not absolutely stable for other values of H. We're going to plot the regions of absolute stability for different methods, but if AH, remember A being the term, the coefficient of U on the right-hand side, we're assuming a linear problem still, and H is the step size, then if AH is such that all of the roots of this characteristic polynomial are less than or equal to 1 in absolute value, then the much better error bound holds that does not have the exponential term in it. So in other words, if you have a stiff problem, that means A is large and negative. Basically there's no hope unless this error bound holds. The other error bound is just too large, doesn't do any good. This one doesn't have the exponential term in it, so if you're solving a stiff system, AH had better be in the region of absolute stability or it acts as if it's unstable. Now on page 45 are plotted the regions of absolute stability for some of the explicit Adams method. M equals 1 is actually Euler's method. M equals 3 is the one we were just using in our example. And these methods are stable inside the closed curve. Euler's method, for example, is stable if AH is inside this closed curve. Now notice this is assuming A is complex. We have the imaginary part of AH and the real part of AH. Of course, H will be real, and in our single equations, A is normally going to be real also, so we're really talking about only the line here. However, there are reasons why we're allowing A to be complex that we'll talk about in just a minute. But in any case, if you're solving a stiff problem, then that means A is large and negative. Then you see H has to be extremely small in order for AH to be inside the region of absolute stability. This would be for Euler's method, this is for the third order Adams explicit method. So for our problem, AH has to be inside this region of absolute stability, and in fact if you check the results we saw a minute ago, you'll find that it's exactly when H becomes small enough so that AH is inside the region of absolute stability that it suddenly goes from being terrible to good. The error bound, which has the huge exponential term in it, applies outside when AH is not in the region of absolute stability. As soon as H is small enough so that AH is in the region of absolute stability, then the other error bound without the exponential term applies, and you have very reasonable error and everything works fine. So you can see that really none of the explicit Adams methods are very good for stiff systems, because a stiff system has a large negative A, and that means that H has to be very small before AH becomes in the region of absolute stability, and until that happens it's a totally worthless method. Problem 4 shows that the same thing applies for all explicit methods, not just the explicit Adams method, but any explicit method cannot work well on stiff systems. It's going to have the same behavior of terrible results, overflow, until H becomes very small. Now, why did we plot the regions of absolute stability for these methods in the complex plane? In other words, why did we assume A might be complex? Normally, we're not going to be solving a single equation, u prime equals AU plus alpha of t, where A is complex. However, we may be solving a system of equations, u prime equals matrix A times u plus alpha of t, where alpha and u are vectors, A is a matrix. In this case, you can reduce this to you can separate it into single equations with the eigenvalues being taking the place of the A, and the eigenvalues of a real matrix may be complex. Therefore, we allow for the possibility that A might be complex. And by the way, stiff systems are going to be very important in the coming chapters. That's why we're talking so much about them. We're going to encounter stiff systems when we solve PDEs, and so it's important to learn how to solve stiff problems, stiff systems efficiently. We've just seen that no explicit method can hope to do well on stiff systems. What methods do work well on stiff systems? Well, a family of multi-step methods that work very well for stiff systems are the backwards difference methods. These methods basically choose beta 0 equal non-zero and all the other betas equal to 0. In other words, the right-hand side is always going to be just f of tk plus 1 comma u of tk plus 1. The beta 1 and beta 2 and so forth are going to be 0. So for all the backwards difference methods, the right-hand side is just a constant times f at tk plus 1. And then the alphas are chosen to make the truncation error as high order as possible. So these are obviously implicit methods because the beta 0 is not 0. They're stable. Actually, only the first 6 are stable. After that, they're unstable, so you don't want to use backwards difference methods of order 7 or more, but the first 6 are stable. And the reason they work well for stiff systems can be seen by looking at their regions of absolute stability. And on page 49, we see the regions of absolute stability for the backwards difference methods. Notice that the regions of absolute stability are the regions outside the closed curves. With the explicit methods, they were inside the closed curve. But here, for example, a backwards Euler, which is a backwards difference method with m equal to 1, is absolutely stable outside of this little circle here. Notice that they all are stable for all negative values of AH. That means, so all the way out here, A can be huge and negative, and H can be large also, so that AH is large and negative, and they're still absolutely stable. So that's why these methods work well. A method that is good for stiff systems, stiff problems, should be one that has a region of absolute stability that extends far infinitely out into the left negative real part of AH plane, and all the backwards difference methods fill that bill. So now if you have a large negative A, as in our previous example, H can be moderate size, 0.1, 0.01, and AH will still be large and negative, but it's no problem because you're still in the region of absolute stability. If you were solving the same problem with an explicit method, AH would be way out here, and it would not be in the region of absolute stability. So now let's go back and look at what happens when we apply the third order backwards difference method to that stiff problem that we looked at earlier. So again, we're solving this problem. Again, A is minus 1,000, so that the error bound that we looked at earlier, which has the exponential term in it, is huge, and it's only when AH is in the region of absolute stability that the method will work. But when we apply the third order backwards difference method to that problem, you see the results are just fine even with large h. With the explicit method, you had terrible results. Remember, A is minus 1,000. Until h gets small enough so that AH is inside the region of absolute stability, you get total garbage, then suddenly it's good. The backwards difference methods, for all h, AH is in the region of absolute stability, and so it works just fine even for large h. and there's no reason why it shouldn't. Remember, the solution is just basically constant times the sine of t. There's no reason why you should have to take such a small step size. You really should use a backwards difference method so that you don't have to take a ridiculously small step size. Okay, now let's go to section 1.6 is about Runge-Kutta methods. These are not multi-step methods. They're very popular among engineers. They're easy to program. They're one-step methods, so they're self-starting. You don't need to use another method to start them. In fact, Runge-Kutta methods can often be used to start the multi-step methods. The Runge-Kutta methods are one-step methods. By the way, that also makes them easier to vary the step size, as we'll see. Easier than the multi-step methods, which assume a constant step size and require some extra work to change the step size. They're hard to analyze, though. Truncation error is very difficult computation, so we're not even going to try to analyze them or calculate the truncation error, except for the simplest case. But here's a popular Runge-Kutta fourth order method. It's easy to program, and there's the 5 lines. Put it inside a do loop and you've got it. But they work just fine. Here are the results when this fourth order Runge-Kutta method is applied to our old problem u prime equals 2t times 1 plus u square. That's the same problem we solved with Euler's method and the explicit Adams methods, or predictor corrector methods, and use the same step size as before, and now the results are even better than the fourth order explicit methods. Get very good results here. The error goes down by a factor of about 16 when h is cut by a factor of 2, which is consistent with the fourth order method. So for this problem, this fourth order Runge-Kutta method works just fine. However, when we apply it to our stiff problem, as you might expect, Runge-Kutta, despite the fact that it's not a multi-step method and thus it's harder to analyze, it's explicit, and as you might expect, it does terrible for the stiff problem, at least the same symptoms as the other explicit methods. Until h reaches a certain threshold, it appears to be unstable, then it works just fine. Now, a good method for solving differential equations should be adaptive. Just like a good quadrature method should be adaptive, it should adjust the step size according to the problem. A good differential equation solver should be able to vary the step size automatically. As I said, that's a lot easier to do for the one-step methods like Runge-Kutta than for the multi-step methods, although it can be done there also. In the book is a very simple adaptive Runge-Kutta method, which basically all adaptive methods use 2 different methods. Every step they take, they use 2 different methods and compare the solutions, and if the 2 different methods give results that are almost the same, the step size is assumed to be good, and you go on. If the 2 different methods give results that differ by a large amount, then you assume that neither one of them is good, and you back up not to the beginning but to the previous step and cut the step size probably by half. That's what this method does. You cut the step size by half and try again, and this Runge-Kutta method is basically 2 different Runge-Kutta methods. Every step it tries both of them. It's a 5th and a 6th order Runge-Kutta method, I believe, and so it's basically getting 2 opinions on the solution, and if the 2 opinions, the 2 methods agree very accurately to within the user's specified tolerance, then it accepts the step size and goes on to the next step. If, however, the 2 different methods disagree, You see, here's the E is the difference between the actually it's fourth order and fifth order Runge-Kutta methods. If that is less than the user supplied tolerance, then rather if it's greater than the user supplied tolerance, it cuts the step size by half and goes back to the beginning, not the beginning of the whole problem, but the beginning of the step, and tries again. If the error is smaller than the user requested tolerance, then everything's fine. If it's way smaller, in this case, if it's like less than 1% of the user tolerance, then it reasons that the step size is unnecessarily small. We're getting too small of an error, and then he doubles the step size for the next time. So very simple primitive adaptive method. Basically adaptive methods for differential equations as well as quadrature methods involve taking two opinions. Every step you either use two different methods, or in some cases you use the same method but with different sub-step sizes. Anyway, you have two methods and you compare the results. If they agree well with each other, then you assume that everything's fine and go on and maybe even increase the step size if the agreement is too good. If the agreement is not good, then you go back and retake it with a smaller step size. So the method should automatically adjust the step size to be small where it needs to be small and large where it doesn't need to be large. Now we try it out on this problem here, which is rigged so that the exact solution is the arctangent of 1000t. Now that's a I don't have a plot of it here, but it's a function which varies very rapidly near zero. It's almost minus pi over 2 until you get very close to zero, and then it jumps up real fast to plus pi over 2, and then it's flat there. So a good adaptive method should take small step sizes near the origin and large step sizes otherwise, and that's just what this method does. Here are the results. We started at minus 1. Go to 1, and you can see that it's taking large step sizes here until it gets close to 0, then very small step sizes, then it increases the step size again because it sees the solution's not changing much. And the error at 1 is 0.0015. So it took about 30. It took about 20 step sizes, not uniform step sizes. It took large ones toward the beginning and the end, and small ones near the middle and 0. But it took about 20 step sizes. So I went back and forced the routine to use a constant step size, 20 step sizes of the uniform steps, and the error then was about 2,000 times larger. In other words, using a uniform step size, the same number of steps, same method, same amount of work, produced about 2,000 times larger error than the adaptive method, which used the same number of steps, same methods, but it made the step size small where it needed to be small and large where it didn't need to be small, and cut the error by a factor of 2,000 without any extra cost.